Hello, this is Dr. Hanaa Assil, and this is about redox equilibria. So that we're talking about electrochemical cells and oxidation reduction equilibria. This is about Unit 5 in the International A2 Chemistry Edexcel, but it could apply to any chapter on electrochemical cells. So let's take a look at what we're talking about. If we put a metal into a solution of its ions, so for example, I have copper metal in copper sulfate solution. Now, there will be an electrical potential or a voltage that is formed between the metal and its ions. So, we're going to put a copper rod, for example, in aqueous solutions of copper ions. This system is called a copper 2 plus copper half cell. So, this is called a copper half cell. Now, in this system, two possible reactions may occur. Either the copper metal will lose electrons and become copper ions, or the copper ions will gain electrons and become copper solid. So which of these reactions occurs? Now, we should know that copper is a relatively unreactive metal, so it is easily reduced. So copper will tend to take electrons or gain electrons from the copper to form copper metal, and that means that in this half cell, this would be usually the reaction that occurs if we have this setup of copper in copper ions. But if I have a more reactive metal, for example, vanadium or zinc or something that is more reactive, or sodium, then these will tend to lose electrons easily. So they're less easily reduced. They tend to lose electrons. So they're good reducing agents. So metals that release electrons are good reducing agents. Now, if I compare the voltage of each metal, I can arrange the metals or the ions in order of their reducing power. Now, how do we measure this reducing power? We measure it using a standard hydrogen electrode. So, what is a standard hydrogen electrode? It is this kind of setup in which I have hydrogen gas at a pressure of 1 atmosphere, and I have a platinum wire attached to a platinum electrode. The platinum electrode is covered with what we call platinum black. So the platinum electrode is in contact with both the hydrogen gas and a solution in the container, which is a strong acid like sulfuric acid of concentration 1 mole per decimeter cubed. So we have hydrogen gas in hydrogen ions, and the platinum black, first of all, is what we call finely divided platinum. So we need this finely divided platinum or the platinum black on the platinum electrode because platinum acts as a catalyst. So this will allow equilibrium between the gas and the solution to be established quickly. It allows larger surface area for close contact of the gas with the H plus ions. And of course, platinum is inert, so it does not take part in the reaction. So when we have this hydrogen, standard hydrogen electrode, the half equation is 2H plus 2 electrons to give hydrogen. Now that means that when we connect this electrode to another half cell, either the H plus ions in solution will gain electrons and become hydrogen gas, or the other way around, the hydrogen gas loses electrons and becomes H plus ions. Now, the electrode potential for the hydrogen electrode is set at 0.00. So the E naught, which is the electrode potential for the half cell, for hydrogen, standard hydrogen electrode, this is given a value of 0. And then we can arrange the others either positive, more than 0, or negative, less than 0. So when a metal is connected to the standard hydrogen electrode, the voltage measured is called the standard electrode potential for that half cell or for that metal. That means standard electrode potential is the potential of the electrode compared to that of standard hydrogen electrode under standard conditions. What are the standard conditions? The ions, any ions in the half cell will have a concentration of 1 mole per decimeter cubed. The temperature is 298 K or 25 degrees Celsius, and the pressure is 101 kilopascal or 1 atmosphere. So this is the kind of setup that we're going to be talking about. In one half cell, we have hydrogen with the platinum electrode in a solution of acid at 1 mole per decimeter cubed. In the other half cell, we're going to have something else like a metal, copper in copper ions, for example. And of course, also the solution has to be 1 mole per decimeter cubed. Now, these are connected by a wire and a voltmeter that is going to measure the voltage. They are also connected by what we call a salt bridge. A salt bridge is a inverted U-tube that contains a solution of ions, for example, potassium nitrate solution. This allows the flow of positive and negative ions between the solutions to connect the circuit together so that there is a voltage to be measured. Standard electrode potentials can be measured for what? Either I have metals in contact with their ions, like the one we talked about, copper in copper ions, or non-metals in contact with their ions, or ions of the same element at different oxidation states. And we're going to talk about each of these conditions. So for example, if we're talking about a metal ion half cell, something like copper in copper ions, this is a half cell, we connect it to a standard hydrogen electrode. If we do that, we find that the voltage measured is plus 0.34. Of course, we give hydrogen a voltage of 0, so that means that the 0.34 is the voltage of the copper ion half cell. And if the voltage is positive, that means that the copper ions are easier to reduce than the H plus ions. That means if I have the hydrogen and the copper ions are more likely to gain electrons. So there is a flow of electrons from the hydrogen cell to the copper half cell, and that means the reduction happens in the copper. And that means the copper 2 plus will gain electrons to become copper, while in the other half cell, the hydrogen loses electrons and becomes H plus ions. Now that means that the overall reaction, what has happened? The copper ions have reacted with the hydrogen to give copper plus 2H plus. Of course, when we add up these two half equations, ionic half equations, the electrons cancel and we get this overall ionic equation. Okay, what happens when we put zinc in zinc ions and then we connect it to the standard hydrogen electrode? We will find that the voltage measured is minus 0.76 volts. That means that the zinc ions are less likely to gain electrons, and that means the electrons will flow from the zinc to the hydrogen half cell. And that means in the zinc half cell, we have zinc losing electrons, becoming zinc 2 plus. These electrons flow through the wire to the hydrogen. The H plus ions take up electrons and become hydrogen gas. Or we could have nonmetals in nonmetal ions. So for example, chlorine in chlorine ions, chloride ions. So if we don't half cells do not contain a metal, then we need an electrode that is a metal. So in that case, the electrode would be a platinum electrode. So remember that if we have the half cell, for example, a chlorine gas in chloride ions, or a nonmetal in a nonmetal ion, then we must have an electrode somewhere. The electrode would be a platinum electrode. And the redox equilibrium is formed on the surface of the platinum electrode. Now, in the chlorine chloride half cell, when we connect it to the hydrogen electrode, we find that the voltage is plus 1.36, and that means that the chlorine will gain electrons and become chloride ions, while the hydrogen loses electrons and becomes H plus ions. Remember that when the voltage is more positive, then that is the one that is more likely to gain electrons. Half cells containing ions of the same element in different oxidation states. For example, I have a half cell in which I have an equilibrium between ion 2 plus and ion 3 plus. Now, when we have this, remember that the solutions, first of all, must have a concentration of 1 mole per decimeter cube each. So I need ion 2 plus with a concentration of 1 mole, ion 3 plus concentration of 1 mole. These are mixed together. So remember that we need to take into account the dilution when we're talking about concentrations. But anyway, all the solutions have to be concentration 1 mole per decimeter cubed. The iron 3 plus with the iron 2 plus need an electrode, so we have to put platinum electrode there, and the concentration of the ions have to be 1 mole per decimeter cubed. Now, if we do this with the hydrogen electrode, the standard hydrogen electrode, we find that the voltage is plus 0.77, plus, we said, the more the positive the E cell, the more this would be a reduction reaction. That means the ion 3 plus will be gaining electrons and becoming ion 2 plus. So remember that when the E note for a half cell is more positive, that means that is where we have reduction. This is where we have gain of electrons. So label, this is a typical question, label the diagram of the standard hydrogen electrode indicating the essential conditions associated with each substance used. Do you remember what we said about the standard hydrogen electrode? We said it will have a platinum electrode and the solution is what? Remember that the solution we said is a strong acid like sulfuric acid with concentration 1 mole per decimeter cubed. Now, what is going in that arrow? Remember, this is a standard hydrogen electrode. We have hydrogen gas going in at a pressure of 1 atm. The platinum electrode of the standard hydrogen electrode is coated in finely divided platinum, which we called platinum black. So just why platinum is used as the electrode and why it is coated in platinum black? Well, what did we say? We said platinum is inert and does not take part in the reaction, and that's why we use it as the electrode. Now, why is it coated in platinum black? Remember, we said the platinum black allows larger surface area for close contact of the hydrogen gas and the H plus ions in solution. State the value assigned to the electrode potential of the standard hydrogen electrode. Remember, we said the E note for the standard hydrogen electrode is given a value of what? Of 0. Remember, the E note for the standard hydrogen electrode is 0. Explain why a reference electrode is needed to measure the electrode potentials. Why do we have to compare each half cell to the standard hydrogen electrode? Because a potential difference requires a complete circuit with 2 electrodes. We cannot measure just the potential for just one half cell. Okay, this is another question, and he is saying the half equation is this, and the standard electrode potential is measured using this apparatus. The measurement is made under standard conditions. Identify the substances needed. In the salt bridge, so we said the salt bridge, which is A, is something that contains a solution of what, for example? We said it has to be a solution of soluble ions, so potassium nitrate is usually the case. And in the right-hand half cell to measure the standard electrode potential. So the electrode in B is made of what? It's made of, what is he doing? He's measuring the half cell for the iron 3, iron 2, and that means I have a mixture of solutions, and that means my electrode is platinum. And the solution contains iron 2 and iron 3 ions. This is another question, and he's saying the standard reduction potentials of two systems are this. What are the components of the half cell required to measure the standard reduction potential of iron 3 plus, iron 2 plus system? Okay, we said the first one is the ions in solution. What do we have in the ions in solution? If we're measuring the reduction potential of iron 3 plus and iron 2 plus system, then we have iron 2 plus and iron 3 plus, right? So my answer is C or D. Now we said what would be the electrode? We said if we have a mixture of solutions of the same element in different oxidation states, then the electrode has to be what? The electrode has to be platinum. Okay, remember when we have iron 2 plus, iron 3 plus, a mixture of solutions, then we need a platinum electrode because the platinum is inert and will not take part in the reaction. Which electrode and solution would be used to measure the standard electrode potential of manganese 3 and manganese 2? Of course, this again is a mixture of ions, so my electrode has to be platinum. Now, what would be the concentration of the solution? Remember, we said if we have solutions of the same element in different oxidation states, then the concentration of each of them has to be 1 mole per decimeter cubed. Okay? The standard hydrogen electrode uses an electrode of platinum coated in a finely divided form of the metal called platinum black. What is the purpose of this coating? We said, why do we use platinum black? Remember that we said this is to increase the rate of equilibrium between the hydrogen gas and the hydrogen ions. This is another question. He's saying apparatus shown is used to measure the standard electrode potential for. So we have dichromate ions and chromium 3 plus ions. Which material should be used for each electrode? Now, electrode 1 is the one in the hydrogen, standard hydrogen electrode, and we said the standard hydrogen electrode has platinum. What about the second electrode where we have dichromate solution with chromium 3 plus? Again, this is a mixture of ions in different oxidation states. Then our electrode also would be platinum. Okay? Solution 1 is what? So, solution 1, of course, is a solution of the standard hydrogen electrode. And we said the standard hydrogen electrode has to be in what kind of solution? It has to be in strong acid and 1 mole per decimeter cubed. So that would be the solution in 1. Okay, so what is an electrochemical cell? An electrochemical cell is set up when we connect two half cells together. So for example, I have a zinc half cell, zinc ions, and a copper half cell, copper ions. Now, what is going to happen? Where will we have loss of electrons or gain of electrons? Where is oxidation and where is reduction? Remember that we already know that zinc is a more reactive metal than copper, and usually the zinc would lose electrons. So that is oxidation, and that means that, remember that oxidation always happens at the anode. So that would be my anode. The zinc electrode would be my anode. And at that anode, the zinc is losing electrons. So I have an accumulation of electrons. And that means the zinc would be a negative electrode. Now, the electrons will move to the copper. And that means the copper now is a positive electrode. This is where reduction happens. So this is the cathode. And that means that the zinc loses electrons. The electrons flow through the wire to the copper electrode, where we have a positive electrode, and that means the copper ions in solution will gain electrons and become copper. Oxidation happens at the anode, reduction happens at the cathode. And remember that this is an electrochemical cell, so the signs for the anode and the cathode are not the same as when we talk about electrolysis. So the anode here is negative, the zinc loses electrons and the electrons accumulate on that side of the wire. The electrons flow through the wire from the more reactive metal, which is zinc, to the less reactive metal, which is copper. Wires connecting the metal rods allow flow of electrons. The electrons released by the zinc pass through the wire and to be used up in the reduction in the other half cell. Remember that we said these two half cells are connected by what we call a salt bridge. The salt bridge allows movement of ions between the two solutions. It's usually a U-shaped tube that contains electrolyte solution, or a strip of filter paper soaked in a saturated solution of potassium nitrate, which is the usual solution that we use. A list of reduction potentials is provided into the data booklet. So at the end of your exam, you have a data booklet where you have a list of the reduction potentials. Now, in order to determine what is the overall potential for a cell, I need to add the E for the oxidation and the E for the reduction. And that means from the data booklet, if all of them are reduction, then one of them has to be reversed. Remember that if I reverse the reaction, then I reverse the sign for E that we're using. So anyway, you need to determine the E oxidation plus the E reduction. That is the overall E of the cell. Now, if the overall potential of the cell is positive, then the reaction is feasible, or it can occur. If the overall cell potential is negative, then we say that this reaction is not feasible. Okay, this is what you have in your data booklet. It's a list of the different ions with their reduction potential. So all of these are reduction potentials. So for example, this is the potential when the sodium ion gains electrons. Remember that all of this is with respect to the hydrogen electrode that is given a reduction potential of 0. Any metal more reactive will have a negative reduction potential, and that means that it is a better reducing agent, tends to lose electrons. So the ones with the low reduction potentials or negative reduction potentials are more likely to lose electrons. The one with the higher reduction potentials are the ones that are more easily reduced, so they are the ones that will tend to gain. When we have two of these and we're comparing the E note, remember, the one that is more positive is the one that is likely to gain electrons. Okay, so in this electrochemical cell that we were talking about, where we have zinc in zinc sulfate and copper in copper sulfate, we look at the data booklet and we find that the E note for these equations are this. So for the zinc, to gain electrons, the potential is minus 0.76. For the copper ions to gain electrons, the potential is plus 0.34, and that means the E note for the copper half cell is more positive, and that means that zinc is more reactive reducing agent, and that means the zinc is more likely to lose electrons, while the copper would gain electrons. And that means actually what happens when you put the zinc with the copper half cells, what happens is actually the zinc loses electrons. So we have to invert that equation for zinc. When we do that, we have also to invert the sign for the E note. So instead of minus 0.76, it is now plus 0.76. And the copper 2 plus is the reduction potential, that was plus 0.34, and that means the overall E note for the overall reaction is plus 1.10 volts. It is a positive E note. That means this reaction is feasible. Do we understand this? So we need to decide the one that is more positive is the one that gains electrons. The one that is less or negative, that will lose electrons. So we need to invert one of them. That means we need to invert the sign of the E note, and the E of the cell is the total of the E for the oxidation plus the E for reduction. And that means that in this setup, where we have zinc in zinc sulfate and copper in copper sulfate, the zinc loses electrons, the copper ions gain electrons, so the overall equation is this. And we said that means that the zinc is the anode and it's the negative. This is where oxidation happens. The copper is the cathode, and that is where reduction happens, and that's the positive electrode. Now, there is a conventional representation of the cell. When we want to represent this cell, instead of saying there is a salt bridge and there is zinc in zinc sulfate and things like that, we write it in a certain conventional representation. This is how we represent this cell. And we start on the left with the oxidation. So what happened in the oxidation? The zinc metal or zinc solid changed to zinc 2 plus. And then we have a salt bridge that is indicated with that double line. And then the copper 2 plus was reduced to copper. And that means that you have, on the left, you have the oxidation, where we have oxidation, and on the right, we have where we have reduction, and you have a double line in the middle to indicate the salt bridge. This is called the conventional representation of the cell. Okay, what if we have this kind of cell? We have copper in copper ions on one side, and we have iron 2 and iron 3 solutions with a platinum electrode. Now, when we have these kinds of half equations, we look at the data booklet and we find these numbers. Now, that means that which one here is more positive? The E note for iron 3 to iron 2 is more positive. And that means that this is where we have gain of electrons. So the electrons will be lost from the copper. So that first equation has to be inverted. It is the copper that will lose electrons. The iron 3 plus will gain electrons. And we said if we invert the equation for the copper, we need to invert the sign for the E note. Adding them up, the E note of the cell comes to be plus 0.43, and this would be the representation of the cell. Notice that, again, on the left we put where we have oxidation. So the copper solid was oxidized to copper 2 plus. Then we have a salt bridge. On the other side now, what do we have? We have iron 2 and iron 3 in solution. And then we have the platinum electrode. So this is how we write the conventional representation of the cell. What if we have this kind of reaction, zinc plus silver ions to give zinc 2 plus plus silver, and we want to know if this is feasible or not? Well, we look at the two half equations. He already tells me that the zinc has to be from zinc to zinc 2 plus, The Ag plus has to be from Ag plus to Ag, so that is where you have reduction. We look at the data booklet and we invert the one for the zinc, so the overall E cell is plus, and that means that the reaction is feasible or spontaneous since the E cell is positive. This would be the representation of the cell. Okay, please get used to all of this. Note that in some cases a reaction may be feasible, so we can say, okay, the E naught is positive and the reaction is feasible, but actually it is too slow to actually occur. In that case, then it must be because the activation energy is too high. Remember that the E naught of a cell is proportional to what? It is proportional to ln K. Do you remember the equilibrium constant? And it is proportional to delta S total. Delta S total was what? The entropy, the total and change in entropy of the cell. So the E naught is proportional to ln K and to delta S. And that means if the E naught of a cell is positive, then ln K is positive and delta S total is positive. So let's take a look at this question. Which statement about E naught for a cell reaction is true? So which one of these is correct? Is it proportional to ln K? Yes, E naught is proportional to ln K, not to K. And it is proportional to delta S total, not ln delta S total, or natural log of delta S total. The value of E cell for a reaction is positive. If it is positive, it can be deduced that what? Well, out of these choices, the total delta S total must be positive, not the delta S system or the delta S surroundings, it's the delta S total. Okay, will iodine oxidize silver to silver ion? So if I have this equation, I look at the E nodes and I arrange them correctly. So this is what I get, and the overall cell potential comes out to be negative. We said if it is negative, that means the reaction is not feasible. This will not occur spontaneously. The standard reduction potential of two systems are this. What is the value of the E cell for the system below? So he's telling me he wants the tin 4 plus to go to tin 2 plus. So that means the E naught is as it is, plus 0.15. He wants the Fe2 plus to go to the Fe3 plus. That means it's the opposite of the one on top, and that means I have to invert the E naught. Now, that when we want to get the overall E cell, then we add these numbers, plus 0.15 minus 0.77. This comes out to be a minus sign. Remember that he got the overall reaction by doing what? By multiplying the equation below by 2, the iron 2 plus to iron 3 plus, we need to multiply by 2 so that both of them have 2 electrons, so that I can cancel the 2 electrons and get that overall equation that he wrote, and that means that my E naught for the cell is minus 0.6. An electrochemical cell is set up to measure E cell for the reaction. Iron solid to iron 2 plus and tin 2 plus to tin solid. What would be the cell diagram? What is the conventional representation of the cell? Well, we need something that starts with iron solid to iron 2 plus, and then tin 2 plus to tin, so that would be this one. Remember, the double line in the middle just indicates the presence of a salt bridge. The standard electrode potential for the iron 2 plus is minus 0.44 volts. And the E for the cell, the overall E for the cell is plus 0.3. So what is the electrode potential for the tin 2 plus electrode system? You know that the E cell is the total of both. So we have this equation, that was the equation we were talking about. Of course, what he gives us is the reduction potential for the iron 2 plus. So the reduction potential for the iron 2 plus is minus 0.44. But actually in my equation, what is happening? The iron is losing electrons. This is an oxidation. So I need to invert the sign for the 0.44. So that is a positive 0.44. Plus the E of the tin 2 plus, that would be the E reduction. Now, overall, it's 0.3. He is looking for the E of the tin 2 plus. That would be the difference between them. So that is minus 0.14. The equation for a redox reaction is this. What is the correct cell diagram to measure the E cell for this reaction? Okay. Where do we have oxidation? We have the Fe2 plus going to the Fe3 plus. And these are a mixture of ions, so we need a platinum electrode. And then we have manganate going to manganese 2 plus. That would need also a platinum electrode. So that would be the cell diagram for this reaction. An electrochemical cell is made from the electrode system shown by these half equations. The apparatus used to measure the value for E cell under standard conditions is shown. Which silver compound could be used as the electrolyte? Remember that the electrolyte here has to be something that is soluble. So which of these is soluble? You should know that all nitrates are soluble, so I should use silver nitrate, not the other compounds. Then he has these two equations. Which is the equation for the overall cell reaction under standard conditions for these two reactions? So if I have these two reactions, I need to decide first which one is oxidation and which one would be reduction. So I look at the E notes. We said, remember, the one with the higher E note is the one that gains electrons. So that means that the silver will lose electrons, and that is oxidation, and that means I need to invert that sign that he gave me. So instead of plus 0.8, I have minus 0.8. And the other one is the reduction with the same E note as it is. Add them all up. Remember that when we add up the reactions, we cancel the electrons on both sides of the arrow, and we write everything on the left and then everything on the right. So the total overall reaction is that one. Okay. Which is the cell diagram for this cell? Well, we have what? We have this, and we said we're going to write this, and that means that we have the silver solid going to silver plus, and then the salt bridge, and the rest, of course, the rest is a mixture of ions, and that means I will need a platinum electrode for that. For this equation, what is the value of the E cell overall? Again, the E cell would be the, remember we said the silver will be inverted, so the silver goes to silver plus, so the E note will be inverted for that. So it is 1 minus the 0.8, so my overall is plus 0.2 volts. Okay, this question is about this reaction. So he has a reaction between iron 3 plus and titanium, and he said the electrode potential for the iron 3 plus is plus 0.77. Again, I'm going to remind you that is the reduction potential. What is the electrode potential for the titanium? So again, he wants in the end the reduction potential for the titanium. Now, what do we have? We have titanium going to titanium 2 plus, so that is oxidation. The iron 3 plus is going to iron 2 plus, so that is reduction. So we write it as it is. E note is plus 0.77. Now, if the overall is 2.4, that means the difference would be 1.63, and that means that the E for that equation, which is oxidation, is plus 1.63. He's asking for the electrode potential, which is the reduction. The reduction will have the opposite sign, so the reduction potential for the titanium electrode system would be the negative 1.63. What metals should be used for the electrodes in the cell for this reaction? We said again, if I have iron 3 plus, iron 2 plus electrode system, these are a mixture of ions of different oxidation states, so the electrode has to be platinum. Now, when we have titanium 2 plus with titanium metal, well, the titanium metal is the electrode. The half cell for the iron 3 plus, iron 2 plus is prepared by mixing equal volumes of solutions of iron 2 and iron 3. What concentrations of the original solutions are needed for the resulting mixture? Remember, we want in the end, we want each of them to have a concentration of 1 mole per decimeter cubed. But then we have a problem. The FeSO4, 1 mole of the solution will have 1 mole of iron. But for the Fe2SO4 the iron 3 sulfate, each mole has 2 moles of iron. And that means if I want them both to be 1 mole and 1 mole, then I must have twice the original concentration of the iron sulfate, so that in the end they will have a 1-to-1 ratio. Did you get that? Okay. A cell could be set up as shown to measure the electrode potential for the reaction between iron 3 sulfate and chromium 2 sulfate. This reaction proceeds spontaneously. So he's telling me that this is feasible or this is spontaneous. So from this, it can be deduced that what? We said if a reaction is spontaneous, then the E cell and the delta S total both must be positive. The reaction between iron 2 and manganate ions was investigated by setting up a cell. Solution A contains iron 2 and iron 3. Now, what is X? Remember we said if we have a solution of ions of different oxidation states, then the electrode is platinum. Then he's saying what is Y? What's Y? Y is the electrode in the other solution. Also, the other solution is manganate ions with manganese 2 plus ions. This is again a mixture of ions in different oxidation states. So again, electrode Y would be platinum. Hydrogen oxygen fuel cell. What's a fuel cell? A fuel cell is a cell in which a fuel gives up electrons at one electrode and oxygen gains electrons at the other electrode. So we have reactants continuously being supplied to the cell. Hydrogen gas and oxygen gas are bubbled in. We have platinum coated electrodes, and what happens is the hydrogen loses electrons and becomes water, for example, and the oxygen electrode, the oxygen gains electrons. Overall, my overall product is water. So overall, the hydrogen and the oxygen are reacting to form water. During that, there is an exchange of electrons. The hydrogen electrode becomes a negative anode, and the oxygen electrode becomes the positive cathode, and this flow of electrons is the electric current. What are the advantages of the fuel cell? Remember that a fuel cell produces only water, so there is no harmful products. It does not produce things like carbon dioxide that will affect climate change or global warming. Also, fuel cells are efficient, produce more energy per gram of the fuel burnt. They are rechargeable and longer battery life. The disadvantages is that the electrodes and membranes are expensive, so this is high cost. Manufacturing these cells involves production of toxic byproducts. High pressure tanks are needed for storage of hydrogen. The hydrogen needed is manufactured from fossil fuels, so we're really using, in the end, we're still using fossil fuels. Fuel cells do not work well at low temperatures. Below zero, the fuel cell will freeze. So let's take a look at some questions. In hydrogen-oxygen fuel cell, the oxygen is what? We said in the hydrogen-oxygen fuel cell, the oxygen is reduced at the positive electrode. What is the half equation at the negative electrode for the hydrogen-oxygen fuel cell? At the negative electrode, we said that is where the hydrogen loses electrons. Remember that in the equation below, we had to multiply all through by 2 to balance the number of electrons. So that equation in A is before we multiplied everything by 2. Which statement is correct for an alkaline hydrogen-oxygen fuel cell when compared with an acidic hydrogen-oxygen fuel cell? Remember that the alkaline one, the catalyst is more efficient. A hydrogen-oxygen fuel cell is used to provide electric energy for an electric motor in a car. The electrolyte in the fuel cell is acidic. So what is the half equation at the anode? Remember, at the anode, the half equation would be the hydrogen going to H+. Remember that the equation I have is for the alkaline. He wants the equation for the acidic, so that would be the H2 giving H+, plus 2 electrons. Hydrogen-oxygen fuel cells have advantages over methanol-oxygen fuel cells. Which of these is an advantage of the hydrogen-oxygen fuel cell? Remember, we said it does not give out things like carbon dioxide, so it will not contribute to climate change. What is true of a hydrogen-oxygen fuel cell? Well, out of all of these choices, we said what happens? The cathode has a more positive potential than the anode. What happens to hydrogen in the hydrogen-oxygen fuel cell? Again, what happens to the hydrogen? We said the hydrogen is the one that loses electrons, so it is oxidized at the negative electrode. Okay, and that's the end of this chapter. I hope you understood this, and thank you for listening, and please share the video. Thank you very much.